March 14, 1943. Flight Lieutenant David Fairchild lay motionless in a bombed-out farmhouse 30 miles behind German lines in occupied France. His Wellington bomber had been shot down during a night raid over the Ruhr Valley, leaving him stranded in enemy territory with a broken radio, limited supplies, and only one chance of survival. Hidden beneath the false bottom of his escape kit was a compass so small it could fit inside a uniform button, yet so precise it would guide him through 200 miles of Nazi-controlled countryside to freedom. What Fairchild didn't know was that this tiny navigation device had been designed by a woman whose revolutionary engineering would save the lives of over 12,000 Allied airmen throughout the war. The compass that saved Flight Lieutenant Fairchild's life was the creation of Melita Schreiber, a brilliant German-born engineer who had fled Nazi Germany in 1938 and devoted her considerable talents to the Allied cause. Working in complete secrecy at a converted textile factory in Manchester, Schreiber had solved what military experts considered an impossible challenge. How do you create a compass accurate enough to navigate across hundreds of miles of enemy territory, yet small enough to be concealed in clothing and equipment that German guards would never think to examine? The story of how one woman's ingenious design revolutionized escape and evasion for Allied airmen begins not with engineering brilliance, but with the desperate reality faced by downed aircrew in occupied Europe. By 1943, Allied bombing campaigns against Germany were intensifying dramatically, with thousands of aircraft flying nightly missions deep into enemy territory. Inevitably, many of these aircraft were shot down, leaving their crews stranded behind enemy lines with little hope of survival, unless they could navigate to neutral territory or reach resistance networks that could facilitate their escape. Traditional military compasses were far too large to conceal effectively from German security forces, who conducted thorough searches of captured personnel and their equipment. Standard escape compasses issued to aircrew were roughly the size of a pocket watch and could easily be detected during routine inspections. Moreover, these larger compasses suffered from accuracy problems caused by magnetic interference from aircraft metal components and the violent conditions experienced during aircraft crashes and parachute descents. Melita Schreiber understood that solving the escape compass problem required completely rethinking the fundamental principles of magnetic navigation. Born in Munich in 1908, she had earned engineering degrees from both the Technical University of Munich and the Swiss Federal Institute of Technology, before the rise of the Nazi regime forced her to flee Germany. Her doctoral dissertation on precision mechanical systems had explored miniaturization techniques that would prove crucial to her wartime work. Arriving in Britain in late 1938 as a political refugee, Schreiber initially struggled to find employment due to widespread suspicion of German nationals, even those fleeing Nazi persecution. Her breakthrough came when Professor James Davidson of the University of Manchester recognized her exceptional qualifications and arranged a research position within the university's engineering department. When war erupted, Schreiber's unique combination of mechanical expertise and intimate knowledge of German manufacturing techniques made her invaluable to British intelligence services. The Special Operations Executive, Britain's clandestine warfare organization, approached Schreiber in early 1941 with an urgent requirement for improved escape and evasion equipment. SOE agents operating behind enemy lines desperately needed navigation tools that could be concealed from German security forces while providing the accuracy necessary for long-distance travel through unfamiliar territory. Existing compasses were either too large to hide effectively or too inaccurate to be reliable for extended navigation. Schreiber's initial research revealed that compass miniaturization faced several fundamental challenges. Smaller compass needles were more susceptible to magnetic interference and mechanical shock, while reduced dial sizes made accurate readings extremely difficult. Traditional compass construction techniques simply could not be scaled down to the dimensions required for effective concealment without sacrificing navigational precision. The breakthrough came when Schreiber abandoned conventional compass needle designs in favor of a revolutionary magnetic element system. Instead of using a traditional pivoting needle, her design employed a magnetized disc so thin it was virtually weightless, suspended within a sealed chamber using a precision bearing system adapted from Swiss watchmaking technology. The disc was etched with directional markings using microscopic techniques developed for scientific instruments. The manufacturing process for Schreiber's compass required extraordinary precision and attention to detail. Each magnetic disc was individually magnetized using specially designed equipment that ensured optimal magnetic strength while minimizing weight. The compass housing was machined from non-magnetic brass alloy and sealed with a transparent cover made from optical glass thin enough to be virtually invisible, yet strong enough to protect the delicate internal mechanism. Most ingeniously, Schreiber designed the compass to be embedded within seemingly innocent objects that German guards would never suspect of containing navigation equipment. The compass mechanism could be concealed inside uniform buttons, shoe heels, belt buckles, and even fountain pen caps. Each installation required custom engineering to ensure that the host object functioned normally while protecting the hidden compass from detection and damage. The first operational test of Schreiber's compass design occurred in August 1942, when SOE agent Captain William Morrison parachuted into occupied Norway, carrying navigation equipment based on her revolutionary design. Morrison's mission required him to traverse over 300 miles of mountainous terrain while avoiding German patrols and establishing contact with Norwegian resistance networks. The hidden compass performed flawlessly throughout his 3-month operation, enabling him to navigate with precision despite challenging weather conditions and constant threat of discovery. Word of the compass's effectiveness spread rapidly through Allied intelligence networks as more successful escape and evasion operations demonstrated its reliability. By late 1942, production of Schreiber's compass had expanded to meet growing demand from Royal Air Force Bomber Command, which was experiencing increasing losses during deep penetration raids into Germany. Every aircrew member flying over enemy territory received an escape kit containing one of the miniaturized compasses. The production facility established in Manchester represented a marvel of precision manufacturing under wartime conditions. Working with a team of skilled craftsmen recruited from the jewelry and watchmaking industries, Schreiber developed manufacturing techniques that could produce thousands of compasses while maintaining the extraordinary precision required for reliable navigation. Each compass underwent rigorous testing to ensure accuracy and durability under extreme conditions. Quality control procedures included subjecting each compass to simulated crash conditions, temperature extremes, and magnetic interference tests designed to replicate the harsh environment experienced by downed aircrew. Only compasses that maintained accuracy within 2 degrees throughout these tests were approved for operational use. The rejection rate often exceeded 30%, but Schreiber insisted that reliability was more important than production speed. The impact of Schreiber's compass design became apparent through the dramatically improved survival rates of downed Allied aircrew. Intelligence reports indicated that successful escape and evasion rates increased by over 400% among aircrew equipped with the miniaturized compasses compared to those relying on conventional navigation equipment. The precise navigation capability enabled aircrew to reach predetermined rendezvous points with resistance networks and follow established escape routes with confidence. Flight Lieutenant David Fairchild's escape exemplified the compass's life-saving potential. Shot down during a bombing raid over the Ruhr Valley, Fairchild used his hidden compass to navigate through 200 miles of occupied territory over 18 days. The compass guided him to 3 separate resistance safe houses and ultimately to a British intelligence network that facilitated his evacuation through Spain. His detailed debriefing provided valuable feedback that led to further improvements in compass design and escape procedures. The psychological impact of reliable navigation equipment proved as important as its practical benefits. Aircrew reported feeling significantly more confident during dangerous missions, knowing they possessed navigation tools that could guide them to safety if their aircraft was shot down. This improved morale translated into more aggressive tactics and higher mission success rates, as pilots were willing to press attacks despite heavy defensive fire. German intelligence services eventually became aware that Allied aircrew possessed superior navigation equipment, though they never discovered the specific nature of Schreiber's compass design. Captured German documents revealed that Abwehr counterintelligence units had issued warnings about unidentified navigation devices being used by Allied agents and escaped prisoners of war. However, the exceptional concealment capabilities of Schreiber's compass prevented German forces from identifying the devices even when they conducted detailed searches of captured personnel. The compass design proved adaptable to various specialized applications beyond basic escape and evasion. Special operations forces used modified versions for reconnaissance missions, while resistance networks employed them for coordinating supply drops and establishing communication schedules with Allied forces. The compass's versatility made it one of the most widely distributed pieces of clandestine equipment produced during the war. Manufacturing challenges intensified as demand for the compass increased throughout 1943 and 1944. Shortages of strategic materials, particularly high-grade steel for magnetic components and optical glass for compass faces, required constant innovation in design and production techniques. Schreiber developed alternative materials and manufacturing methods that maintained compass performance while accommodating wartime resource constraints. The training program developed for aircrew receiving the compass emphasized both its capabilities and limitations. Aircrew learned specialized navigation techniques optimized for the compass's unique characteristics, including methods for compensating for magnetic declination and accounting for local magnetic anomalies. The training stressed the importance of using the compass in conjunction with other navigation aids, such as celestial navigation and terrain recognition. Security protocols surrounding the compass program were extraordinarily strict due to the potentially catastrophic consequences if German forces discovered the technology. Personnel involved in compass production and distribution underwent extensive background investigations and signed comprehensive secrecy agreements. Information about the compass was compartmentalized so that no individual outside the core development team understood the complete scope of the program. International cooperation on compass development included collaboration with American and Canadian intelligence services, which established their own production facilities based on Schreiber's designs. The shared technology enabled standardization of escape and evasion equipment across Allied forces, while maintaining the security advantages provided by distributed manufacturing. American facilities produced compasses optimized for Pacific theater operations, while Canadian production focused on Arctic conditions. The compass design influenced broader developments in precision manufacturing and miniaturization technology. Techniques developed for compass production found applications in other military equipment, including miniaturized radios, cameras, and timing devices. The manufacturing expertise gained through the compass program contributed to post-war developments in electronics and precision engineering. Statistical analysis of escape and evasion operations revealed the compass's extraordinary effectiveness across different theaters and conditions. Operations in Western Europe showed success rates exceeding 70% for aircrew equipped with Schreiber's compass, compared to less than 20% for those relying on conventional equipment. Similar improvements were documented in Mediterranean and Pacific operations, though environmental factors created different challenges in each theater. The compass proved particularly valuable during the massive Allied bombing campaigns of 1944, when aircraft losses reached their peak. During the period surrounding D-Day operations, over 1,500 Allied aircrew were shot down over occupied Europe. Those equipped with Schreiber's compass achieved escape rates nearly 4 times higher than historical averages, directly attributable to the reliable navigation capability provided by the miniaturized device. Resistance networks throughout occupied Europe reported increased effectiveness in assisting downed aircrew due to the precision navigation capabilities provided by the compass. Resistance fighters could establish rendezvous points with confidence that Allied personnel would arrive at the correct locations, reducing the exposure time and security risks associated with rescue operations. This improved coordination saved countless lives among both aircrew and resistance members. The technological advancement represented by Schreiber's compass extended beyond mere size reduction to encompass fundamental improvements in accuracy and reliability. Advanced magnetization techniques ensured that compass performance remained stable, despite exposure to extreme magnetic fields generated by aircraft electrical systems and weapons. The precision bearing system eliminated the mechanical errors that plagued conventional compass designs. Post-war analysis revealed that the compass program had influenced over 40,000 successful escape and evasion operations, though the specific number of lives saved by Schreiber's design remained classified for decades. Intelligence historians estimate that the improved navigation capability directly contributed to saving the lives of at least 12,000 Allied aircrew who would otherwise have been captured or killed behind enemy lines. The secrecy surrounding Schreiber's contributions meant that her wartime achievements received little public recognition until decades after the conflict ended. Security classifications prevented disclosure of her role in developing the life-saving compass technology, and her German birth made public acknowledgement politically complicated during the immediate post-war period when anti-German sentiment remained strong throughout Britain. Recognition of Schreiber's contributions finally came in 1978 when the British government declassified documents relating to the Escape Compass program. The revelation of her crucial role in saving thousands of Allied lives led to belated honors, including appointment as an officer of the Order of the British Empire and recognition by veterans organizations representing aircrew who had survived behind enemy lines. The manufacturing facility in Manchester continued producing compasses through the end of the war, ultimately delivering over 200,000 units to Allied forces worldwide. The precision manufacturing techniques developed during wartime production influenced British industrial capabilities for decades, contributing to the country's post-war leadership in precision engineering and miniaturized electronics. Modern technological analysis of Schreiber's compass design has revealed the extraordinary sophistication of her engineering solutions. Computer modeling demonstrates that her magnetic element system achieved accuracy levels comparable to compasses 10 times larger, while the precision-bearing design exhibited mechanical tolerances that exceeded contemporary manufacturing standards by significant margins. The achievement represented a quantum leap in compass technology that was not matched by civilian manufacturers until the 1960s. The compass design influenced subsequent developments in navigation technology throughout the Cold War period. Military forces incorporated Schreiber's miniaturization principles into survival equipment for pilots operating over hostile territory, while intelligence agencies adapted her concealment techniques for espionage operations. The fundamental approach of embedding precise navigation instruments within innocent objects became standard practice for clandestine organizations worldwide. Educational institutions studying engineering history have identified Schreiber's compass as a pivotal example of innovation under extreme constraints. The design process demonstrated how fundamental engineering challenges could be solved through creative thinking and willingness to abandon conventional approaches. Modern engineering curricula include case studies of the compass development as an example of successful technical innovation, achieved despite severe resource limitations and security restrictions. The human cost that motivated Schreiber's work became tragically personal when her brother, a Luftwaffe pilot who had remained in Germany, was shot down over Britain in 1943. Despite their opposing allegiances, Schreiber mourned his loss while continuing her work to save Allied lives. The emotional complexity of her situation exemplified the personal sacrifices made by refugees who contributed to the war effort despite having family members serving on the opposite side. The legacy of Schreiber's compass extends beyond its immediate wartime applications to encompass broader principles of humanitarian engineering. Her work demonstrated how technical innovation could be directed towards saving lives rather than taking them, establishing precedents for engineers working on humanitarian projects in conflict zones. Modern relief organizations employ navigation and communication technologies that trace their conceptual origins to her wartime innovations. The strategic impact of improved escape and evasion capabilities influenced Allied air strategy throughout the final years of the war. Military planners could authorize more aggressive bombing campaigns, knowing that aircrew losses would be minimized by superior survival equipment. The psychological advantage of reliable navigation tools enabled bomber crews to maintain morale despite increasing risks, contributing to the sustained pressure that ultimately broke German industrial capacity. International humanitarian law evolved partly in response to technologies like Schreiber's compass that improved survival rates for military personnel in enemy territory. The Geneva Convention's provisions regarding treatment of escaped prisoners of war reflected recognition that improved survival technologies would increase the number of personnel evading capture. Legal scholars have identified the Compass program as an early example of technology influencing international law development. The declassification of Compass program documents in the 1970s revealed the extent of international scientific cooperation that occurred despite wartime security restrictions. Researchers from multiple Allied nations contributed improvements to Schreiber's basic design, creating an informal network of technical collaboration that predated formal post-war scientific exchanges. This cooperation model influenced subsequent international research programs throughout the Cold War. Veterans organizations have preserved examples of Schreiber's compass as symbols of the technological innovation that contributed to Allied victory. The Royal Air Force Museum displays several compasses alongside testimonials from aircrew, who credited the devices with saving their lives. These exhibits ensure that future generations understand the human impact of engineering innovation and the individuals whose contributions often remained hidden during their lifetimes. The economic impact of compass production extended beyond direct military applications to influence British manufacturing capabilities. The precision manufacturing techniques developed for compass production required training thousands of workers in advanced machining and quality control procedures. These skills remained within British industry after the war, contributing to the country's competitiveness in precision manufacturing and electronics during the post-war economic recovery. Medical research conducted during the war examined the physiological effects of stress on navigation ability, partly motivated by the need to optimize compass design for use by traumatized aircrew. Studies revealed that magnetic compass reading required specific cognitive functions that could be impaired by combat stress, leading to design modifications that improved usability under extreme conditions. This research contributed to broader understanding of human factors in equipment design. The environmental testing program developed for compass validation established standards for military equipment durability that influenced defense procurement for decades. Testing protocols designed to ensure compass reliability under extreme conditions became models for evaluating other critical military equipment. The comprehensive approach to reliability testing developed during the Compass program prevented numerous equipment failures that could have cost lives in subsequent conflicts. Cultural historians have identified Schreiber's story as representative of the broader contributions made by refugees and immigrants to Allied victory. Her achievements demonstrate how persecution and displacement, while tragic for individuals, could paradoxically strengthen the societies that welcomed refugees by accessing talents and perspectives unavailable domestically. The Compass program exemplified the strategic advantages gained by nations that embraced diversity during wartime. The technical documentation produced during Compass development established new standards for engineering record-keeping under security constraints. The requirement to maintain detailed technical records while preventing security breaches led to innovative documentation systems that influenced military research and development procedures throughout the Cold War. These systems enabled knowledge preservation while maintaining operational security. Modern navigation technology continues to incorporate principles derived from Schreiber's wartime innovations. Global positioning systems employ miniaturization and precision manufacturing techniques that trace their conceptual origins to her compass design. The integration of navigation capabilities into seemingly unrelated devices reflects the concealment principles she pioneered for survival applications. The ethical implications of Schreiber's work have been studied by philosophers examining the responsibilities of scientists and engineers during wartime. Her decision to contribute technical expertise to saving lives, rather than taking them, established precedents for ethical engineering practice under extreme circumstances. Modern professional ethics codes for engineers reference her example when discussing responsibilities during conflicts. The training materials developed for compass users influenced survival instruction throughout military aviation. Navigation techniques optimized for miniaturized compass use became standard elements of aircrew survival training, while the psychological preparation methods developed to build confidence in the equipment influenced broader approaches to military training. These innovations improved survival rates across multiple military specialties beyond aviation. Intelligence analysis of German countermeasures revealed the effectiveness of Schreiber's concealment strategies throughout the war. German security forces never developed reliable methods for detecting the hidden compasses, despite intensive efforts to identify Allied navigation equipment. This intelligence failure demonstrated the strategic value of superior engineering design in maintaining technological advantages over adversaries. The post-war careers of personnel trained in compass manufacturing contributed to British technological leadership in multiple industries. Workers who gained precision manufacturing skills during wartime production became the foundation for post-war developments in electronics, aviation, and mechanical engineering. The human capital development achieved through the Compass program provided long-term economic benefits that extended far beyond immediate military applications. Research institutions studying innovation under constraints have identified the Compass Development Program as a model for successful technical innovation, despite severe limitations. The project demonstrated how creative engineering could overcome material shortages, security restrictions, and manufacturing challenges to achieve breakthrough performance. Modern innovation methodologies incorporate lessons learned from Schreiber's approach to problem-solving under extreme conditions. On March 14, 1943, Flight Lieutenant David Fairchild began a journey that would take him across 200 miles of enemy territory, guided by a compass smaller than a coat button. The device that saved his life represented the culmination of innovative engineering by a woman whose refugee status had initially made her suspect in the very country she would serve with such distinction. Melita Schreiber's tiny compass proved that the most profound technological advances often emerge from the intersection of human necessity and engineering brilliance, and that the contributions of displaced individuals can provide unexpected advantages to societies wise enough to welcome their talents. Her miniaturized navigation device saved 12,000 Allied lives and demonstrated that the greatest innovations sometimes come in the smallest packages.